All right, welcome in to another video. Only a few more to go for this week. The next topic we're covering is power series. Okay, and what I want to draw attention to before we get into some examples is, all right, well, first, what does a general abstract power series look like? Right, so it looks as if the sum from n equals 1 to infinity, right, all infinite series, we have a sub n, which is just some constant, and then it's going to be x minus some value a raised to the n. Now, this a here, right, is again just a value, so these two are values. This is a value, like a number. This is also a number over here, right? Notice this one, however, is getting incremented, so that means it can change over time. This value stays the same. So if you write out a couple terms here just to get the idea, this is a1 x minus, sometimes it'll start at 1, sometimes it'll start at 0. We'll just start this one at 1. Minus a to the first power plus, let's do a2 x minus a to the second power plus dot dot dot. This keeps going, right? And so what do we notice is that from this instance to this one, what are we doing, right? Well, the constants are changing, right? a1 and a2, but also we're multiplying by an extra x minus a, right? So hopefully this brings a little bit of familiarity with the geometric series, right, that we already talked about. Right, so I'll write this here, geometric series. Okay. Just so again we see the comparison between the two, let's do n equals 1 to infinity, and this is an abstract geometric series where we have a, right? Notice that this a is not changing, it's just a constant. And then we have r raised to the n power, where r here is our common ratio. And if you're like, well, what is common ratio? Maybe we need to go back and watch the geometric series one. Right, so if you don't know what a geometric series is, the connection between these two is going to be a little bit difficult. Right, so notice here, if we write out a few terms, we have r plus a r squared plus dot dot dot. Right, so the only difference here is, notice between here and here we're multiplying by r. Right, so it's a very similar pattern, right? From here to here I'm multiplying by r. From here to here I'm multiplying by x minus a. So we have this same kind of thought process on convergence, right? So if we remember for r, right, for geometric series, we say we converge, this is our rule, we converge if r is between 1 and negative 1. Right, so we're going to take this knowledge and use it up here, right, with our power series. Now, we haven't gotten into any examples. We will do that in the next pause. I just wanted to introduce the concept, right? We will converge using this same kind of idea up here, but tying these two together won't happen until we actually do an example, and you can see how they connect, right? So this is the general idea of a power series, right? It's going to take on a bunch of different forms. We're going to introduce two rules, right? So you'll see in the next sections, there's normally two different ways on solving a power series. We have what's called the ratio test and the root test. There might be some other ways, but for us, these are the only two ways that we're going to introduce, right? So ratio test and root test are going to be our main two things. All right, I'm going to wipe off the board. We'll do an example first of the ratio test, and then we'll go to the root test. So I will see you shortly in the next part. Okay, so with our example of ratio test, right, first we need to know, well, what is the ratio test? That would be helpful. So the ratio test tells us that if we take the limit as, let's say, k, and we'll get to where this k came from in a second, k goes to infinity of the absolute value of a to the k plus 1 over a to the k. Right, so again, we'll specify all this once we get into example, and it's going to be equal to a limit. Right, so essentially is we're going to take the next term, right, and divide it by the current term. Right, so again, let's leave this here for a second. We're going to have some rules, right, for L. We're going to say if L is less than 1, we will converge. Right, and you should see hopefully how from the geometric test or the geometric series, right, if our R is less than 1, we converge, right? And it's the same thing here, right? We have the absolute value signs here, so really if it's between these two values, -1, or let's get rid of that, -1 and 1. But again, since we have the absolute value, we're only going to really be dealing with the +1. So if it's less than 1, it converges. If L is greater than 1, it diverges, and if it's equal to 1, we don't know. We have to do more stuff. So L is equal to 1, I don't know. More steps to follow. Okay? All right, so all of this looks a little bit foreign. I want us to write it down so that now when we're getting into our example here, we'll be able to utilize this. Okay, so example 1. I'll try to move out of the way. Right, let's say I give you the infinite sum starting at n is equal to 1. It's going to be, what is it? 3, or sorry, let me erase, that's fine. X to the 3n plus 4 all over n factorial. Right, so this kind of looks like one in your problem. I'm actually taking it a step back further than what they have. So in order to find, right, the limit, right, remember our step around, we have to take the partial sum. So essentially we end up translating this, right? Instead of writing infinity, I want the limit as k goes to infinity, right? And we have, I'm going to rewrite this first, right? The sum from n equals 1 to k, and this is now going to be still x to the 3n plus 4 all over n factorial. Okay. Right, so again, I took it back a step further. I think in your homework it immediately gives you this. Now, the ratio test is saying, right, if we take the next term in our sequence, right, so k plus 1, right, so meaning we're going to leave this limit here, and we're going to do to k goes to infinity. And now we'll take the absolute value, and instead of plugging in an n, right, we're going to plug in the k plus 1. Right, so this will be x3, we plug in k plus 1 instead, plus 4, and again over here, right, this is also going to be k plus 1 factorial. I'm going to draw this long absolute value sign, right, and we need to divide it by a to the k. Right, well, a to the k is just going to be x to the 3k plus 4 all over k factorial. So we have this weird 4-layered fraction, right? But instead of having a weird 4-layered fraction, we can flip it, right? So it's just an algebra trick to get this to be a regular 2-layered fraction. So we'll say, we'll draw a line here. We'll have the limit as k goes to infinity. That's an infinity. Let's go ahead and separate all this stuff. This ends up being 3 times k, right? So this is going to be x to the 3k plus 7, right? Because 3 times 1 plus 4, all over k plus 1 factorial. And now instead of dividing by this, we'll multiply by the reciprocal. So we end up with a k factorial over x to the 3k plus 4. And I'll pause for a second so you guys can copy that down. So again, instead of dividing by another fraction, we multiply by the reciprocal, so the k factorial flips up here to the numerator and the other one to the denominator. Now from here, we need to know how to make a few cancellations. So this is where we need to kind of lock in and pay attention, because we're going to cancel a few things here. Okay, so what's going to happen, right? You could think of, right, the 3k's are going to cancel out. We're going to be left to an x to the 7th over an x to the 4th. We'll be left with an x cubed. Right, so that's coming from these two here. I'm going to do a little bit of side work to show the other one. Right, so if you're wondering, well, what about the k factorials? Well, remember, if we have k factorial divided by k plus 1 factorial, all that is k plus 1 times k factorial. Right, so both of these are also going to cancel each other out, and I'm just left with a k plus 1. Okay, so notice here, again, this x is a variable, right? So x could be any number, right? Any number that I can plug in. So I do need to pay attention. When I go to plug in this infinity, right? So now I can actually finish taking the limit. Is there any x value, right? So just let's do the easy case. Pick a random arbitrary value, let's say 2, right? If I go to infinity, what is this going to go to, right? Well, this is going to go to 0. So the question is, are there any x values that I can plug in here in which this would not go to 0? And the answer is no, it always goes to 0, right? It always converges. And in the root test, I'll try to find one that does not always converge, so we get another example. So the reason why it always converges, right, because no matter what x value I plug in here, this thing will always go to 0. And remember our rule from over here. We said if our limit is less than 1, we converge, right? Well, we've said this is always going to go to 0. This is always, right, which is less than 1, so it will always converge, right? It will always converge. Now, if it always converges, the interval of convergence is negative infinity to positive infinity, right? Which means, right, so this is the interval of convergence, and the radius of convergence is always just going to be half of our interval, right? So in this case, radius of, I'll just put converge, is just half of our interval, so let's just put infinity. So maybe I'll do one more example of the ratio test so we get a contrast between the two. It's hard just to know off of one. So we'll be right back. We'll do one more ratio test, and then we'll finish off with a root test, which is very similar in theory, right? So keep these here, right? Again, all we're doing is substituting. We're doing the k plus 1 term, right? K plus 1 term divided by the previous term, a to the k. We should be able to make some algebraic simplifications. From there, we're taking the limit as k goes into infinity. In this case, it always goes to 0, right? Which is always less than 1, so it will always converge. If it always converges, we get the whole real number spectrum from negative infinity all the way to positive infinity, which means the radius of convergence is infinity, right? So I'll try to find another one where we can contrast this, where we actually do have a specific interval and a different radius. Perfect. Be right back. Welcome back to the ratio test. So first, before we get into an example, we should know what the ratio test is. So we'll put this on the side. Real quick before I forget, our example is going to be the sum from, let's do n equals 0 to infinity of the square root of n times x minus 1 to the n. So I'll leave the example before I forget it. inside my head. Now the ratio test states, right, if I take the limit as k goes to infinity, right, of the absolute value, and this is the part that is going to look foreign, right, a to the k plus 1 divided by a to the k, right, where a to the k is just some term in here, right? So essentially we're just going to start switching n's for k's. That's all that's going to happen. And k plus 1's for instead of n's over here, right? Whatever we get, we're going to call L, which is the limit, right? So we need to calculate this. And again, we'll go through the steps over here on how we do that. And then our interpretation is, if L is less than 1, we will converge. And there'll be some extra work we have to do, as you can see in your questions, right? What is the interval of convergence, and what is the radius of convergence, right? So we'll talk about that. If L is greater than 1, we diverge. And if L is equal to 1, I decay. We don't know. There's more stuff we have to do. Okay, so let's get into this first part of the problem, right? So how do we even set this up, right? Well, let's just start with the limit as k goes to infinity. And now a sub k plus 1, instead of these n's here, let's make that a little bit, we're just going to switch the n's out with k plus 1's, right? Meaning I'm going to have the absolute value of the square root of k plus 1, right? So these k plus 1's just take the place of the n, times, instead of, we have x minus 1, and instead of raised to the n, it's going to be k plus 1. And now divided by a to the k, so the square root of k, and then it's going to be x minus 1 raised to the k. And of course, close your absolute values. Right, so from here we want to make a few algebraic simplifications, right? Maybe this one is obvious, right? Over here though, what we're going to do is we'll just write it as such, right? They're both under a square root, so let's just write it as one giant square root. And this could be, right, this would be the absolute value on its own, that's fine. And then we can write another one over here, right, because notice it's k, as k goes to infinity, what ends up happening here? I'm going to write it out so we can see it. This is x minus 1 to the k times x minus 1 all over x minus 1 to the k. And so what happens are those two cancel out, and we're left with the limit as k goes to infinity of the square root. And before we move forward, let's make this a little bit easier, because in the future we're going to have to take the limit here, right? So let's just go ahead, we're going to distribute this k to each piece. So k over k is going to be 1 plus 1 over k, right? So I just simplified this, because now when we take the limit of this, this was going to be a little bit easier. And this over here is just x minus 1. Okay, so we're at a pause point, because now what's going to happen here when I plug in infinity? Well, this is going to be 1 plus 1 over infinity. Well, that's going to go to 0, right? We'll just end up with the square root of 1, right? So this will end up just being the square root of 1, which is 1 times x minus 1, right? So this is our limit. We just essentially have x minus 1. Now the question is going to ask, well, where do we converge, right? And what did we say, right? This is x minus 1. This is equal to our limit. And we said, well, we converge, and this is absolute value, just so we're clear. The 1 doesn't matter. Let's pretend this is an absolute value sign, right? We converge if we are less than 1, right? And this is an absolute value, right? So I'm going to draw a line over here. Right, so we found this part. Now it's asking, what is the interval of convergence? This is the question that we're asking and get an answer. Interval of convergence. And again, what we said here is if L is less than 1, and we know that L is the absolute value of x minus 1, meaning x minus 1, I'll draw those a little bit bigger, have to be less than 1, right? Another way of writing this so we can get rid of the absolute value signs is by saying, well, we know that this must be between -1 and +1. And we want to solve for x, right? So how do we solve for x? We need to add 1 to both sides, which means we'll get a 0 and a 2. And that's just how we solve the interval of convergence, right? So I know that I will converge anywhere between 0 and 2. I'm going to converge, right? Anywhere between those two values, my limit is going to be less than 1, which will mean that I will converge anywhere on that interval. Anywhere outside of that interval, right, I will diverge, and anywhere on the bounds itself, right, I don't have an answer for you. Now, if I know the interval of convergence is 0 to 2, I know that the radius of convergence is just going to be half of the interval, right? If I can travel a distance of 2, right, from 0 to 2, my radius is going to be half of that. So radius of convergence, right, essentially all you're doing here is finding the midpoint of your interval, right? Midpoint being 0 plus 2 over 2, we get 1, right? So our radius of convergence is 1, right? The key thing here, right, is applying this, right? So we have our power series, it gives it to us, right? The key part here is knowing that we're supposed to use the ratio test. It's not so easy to recognize at first. The more you do, the easier it is to recognize which one gets the ratio test, right? Those are the two tests we're utilizing are ratio and power. The power is a little bit more obvious, right? We see we have mixed match things here where this is raised to the n, this is the square root of n. Another common one is you'll see over n factorial, right? So those are all possibilities. After that, instead of having n, right, we want to plug in a k plus 1. So that's what we have here in our numerator. And instead of plugging in n, we want to plug in a k. That's what we have in our denominator. We make our simplifications. We take our limit. In this case, we ended up with an x minus 1. So we do want to see where it will converge. And we know that it will converge if L, which is equal to x minus 1, is less than 1, right? We expand and get rid of the absolute value sign. So we're between -1 and +1. We solve for x in the middle. We have 0 and 2. That gives us our interval of convergence. And our radius of convergence is just going to be the half of the distance of the interval. So in this case, just a nice easy one, right? I know I went through that fast. Take your time, watch it again. Come to class with questions, right? There's many different variations of this. So I know these will be difficult questions, but again, feel free to ask as many as possible. I will see you in the root test. Jumping back in with the root test, right? So very similar to the ratio test. I already wrote up the example so I don't forget it. But very similar to the ratio test is the root test. Now, all we're doing here, last time I used k's, you're welcome to use n's as well as a placeholder. But the idea is the limit as n goes to infinity, and we're going to take the nth root of the absolute value of a sub n, right? And it's going to equal a limit L, right? So a little bit different. Again, once we get into an example, this will make sense. But we have the same idea. If L is less than 1, we're going to converge. If L is greater than 1, we will diverge. And if L is equal to 1, we don't know. And when I say I don't know, that means there's other tests for us to perform, right? So that's why I just wrote the shorthand, I don't know, but there are other tests that we would have to perform if our limit was equal to 1, right? So we have our example here. A key indicator of when to use the root test is when we have something on the top and bottom, or just in general, that is just raised to the n, right? And you'll see why that is a key indicator here once we get into the example. So let's write this out. We have the limit as n goes to infinity of the nth root and there's a better way to write this, the nth root, but we'll get to it in a second, of a sub n, right? So we have the absolute value of 2x minus 3 raised to the 4n all over n to the 2n. And so I want to just start to rewrite this. So I'm going to write the limit as n goes to infinity. And instead of writing it as a root, right, I'm going to write it as an exponent. So we're going to say parenthesis, and on the inside, I'm going to write this as another parenthesis here. We're going to have 2x minus 3 over 2x minus 3 to the 4th. Let's do it as such, to the 4th, over n squared right, all raised to the n. There we go. Right, so I pulled an n from here, right, and an n from here, and I've raised the whole thing to an n. Right, so the n would go with this, which we would get the numerator. The n would go with the denominator, we'd get the denominator. And again, this is all raised to the 1 over n. Right, so let's slow this down a little bit. What happened? This root n became this 1 over n. And from the inside, we just pulled out an n from both. Since they're both raised to the n in the exponent, we pulled that out, right? And now what happens is we have this nice cancellation, right? So the reason why this is a key indicator when both of these things are raised to the n power, right, is because if we can factor that out, it's going to cancel out with our root test, which means we just end up with a nice limit. So we just end up with 2x minus 3 to the 4th all over n squared. Right, and what do we notice here is that n is going to get arbitrarily large, right? So it does not matter what x values we plug in here, this thing is going to go to 0, right? So no matter what x value you plug in, this thing is going to go to 0, right? If you don't believe me, again, we're not changing the value of x here. Even though I know it's a variable, we're only changing the value of n, right? We're only changing the value of n. This should be absolute value signs anyways. But again, what we could rewrite this as since we're not changing the value of x, is we could put the 2x minus 3, and this is going to be positive regardless because it's raised to the 4th power. And then we have the limit as n goes to infinity of 1 over n squared, right? Because n is the only thing that is changing, right? That's what we're taking the limit to. Now this is going to go to 0, and if this is 0 and we multiply it over here by 0, the whole thing is going to be equal to 0. Right, so in this case, what did we say? Right, we took our limit, this is equal to L, right? This is our limit, and we said if L is less than 1, we will converge. Well, 0 is less than 1, so we do converge, right? We converge. And the good news is, that makes this problem a little bit easier to work with, is that there was nothing even to solve for the radius of convergence, right? Because no matter what, the limit is always going to be equal to 0. No matter what I plug in here for x, my limit is going to be equal to 0. That means I always converge. And if I always converge, that means my radius of convergence is going to be negative infinity to infinity because I always converge. Or not radius, I'm sorry, interval. The radius of convergence is always going to be half of that interval, right? Which means our radius of convergence is just going to be infinity. Right, so if we ever have something where we get a limit equal to 0 and 0 is always less than 1, that means we're always converging. That means our interval of convergence is our entire real number spectrum, and our radius must mean half of that. So again, I'm going to do more of these in class. We're really going to utilize tomorrow to go through these in class. This is just really more acting as a supplementary. So go through this, watch it a few times. This one is straight out of your homework. But again, feel free to ask as many questions as possible in class, and I will see you guys tomorrow.